Okay, so what we're going to talk about this final week of the course is mostly carboxylic acid type compounds. We can generically call them carboxylic compounds. They are derivatives of carboxylic acids. Now, what we mean by derivatives is that you could think of them as being derived from carboxylic acids. So it's like you start with carboxylic acid and you transform it into these other functional groups. That's what we mean by derivatives of. So carboxylic acid, and then one way to transform it is to take away the OH and put a halogen. Those are called acid halides. A lot of times, if you know what the halide is, you just say acid chloride or acid bromide. Okay, this one is called an anhydride, where you have another carbonyl and another R group instead of the hydrogen. Remember that an ester is when you have another R group off of the oxygen instead of a hydrogen. And then if you replace that OH with a nitrogen, and it can have either two hydrogens, or it can have one carbon group and one hydrogen, or it could have two carbon groups, that's called an amide or an amide. I'm not sure which accent, which syllable gets the accent, but so those are the ones we're going to talk about the most. But these are two other derivatives that you could also talk about, and they are talked about in the textbook, the thioesters. So they're very similar, obviously, to esters, but instead of an oxygen, it has a sulfur. And then the acyl phosphates, which are important in biology. These phosphate type groups are involved in a lot of biochemical reactions, but unfortunately we won't get a lot of time to talk about those, but they are in the textbook, and you will see those in Organic 2 and Biochem if you have to take those courses. Okay. All right, so here we go. So we're going to talk about another type of reaction that carboxylic acids are involved in, and that is called the nucleophilic acyl substitution reactions, abbreviated in the notes today as NASR, because that's a mouthful and a lot to write. So we'll just refer to it as NASR today. So what happens in this type of reaction is that the nucleophile attaches, like we showed with the nucleophilic addition reactions. We already talked about those last week. But in this case, instead of an addition, you get a substitution. So after a nucleophile attaches to a carbonyl atom, the tetrahedral intermediate releases one of the two substituents originally bonded to the carbonyl carbon. So that's illustrated in this diagram right here. So our nucleophile attacks that carbonyl carbon. A pair of electrons get pushed up onto the oxygen to give it a formal negative charge. And so now you have this tetrahedral intermediate. And remember that that's similar to what we had with a nucleophilic addition reaction, like we talked about last week. And so that's why, I have that little side arrow. So let's add something to that. Remember that in that case, if we had something like, some acid present, like H3O plus, okay, then it will just protonate this oxygen. And so you would end up with a carbon, and then you end up with an alcohol group. So that's this acid would protonate that oxygen. And so then you have your R group, and you have your Y group, and you have the nucleophile that's just been added. So that would be the nucleophilic addition reaction like we talked about last week. What we're going to focus on this week is, well, instead of just a permanent addition, if instead you get a substitution where the Y group, which is going to, the Y symbolizes a leaving group, if it leaves, then you go back to this sp2 hybridized carbon with the carbonyl group, and the electrons go back from the oxygen to form that double bond between the carbon and the oxygen. You get the carbonyl back, and then you get, like I said, the Y in this case just served as a leaving group. Okay, so let's do an example. So we're going to show the mechanism of the following nucleophilic acyl substitution reaction. All right. Now, if you don't mind, I'm just going to abbreviate. Remember that this benzene, we can just abbreviate that with a pH. It'd be a little easier if I just write that. So remember that the intermediate is going to be the carbon. Now the electrons move up onto the oxygen. So I get the carbon, the oxygen, and now it's got 3 lone pairs on it. It's got the formal negative charge. Okay. And then the chlorine, we'll say that that's going to be poking out. And then the that phenyl group, which we'll just abbreviate with a pH, the benzene ring. Okay. And what has been added is, this was my nucleophile. So that's my nucleophile. And so that oxygen attacks carbonyl carbon. So that's where I get that OCH3 connected right there. Okay. So in order for this intermediate to transform into our final product there, you think about what needs to happen. Well, a pair of electrons are going to move back to between the oxygen and the carbon to form that double bond right there. And then this pair of electrons connecting the carbon and the chlorine is going to come off and go onto the chlorine. That's going to become a chloride. So that's another product here. Okay. And so also remember that I've got this sodium ion. So it's like I've got sodium chloride as kind of a byproduct. Table salt is kind of a byproduct. But that's the mechanism. So you get a tetrahedral intermediate, but it doesn't stay that way. With the substitution reaction, in this case, that chlorine leaves, acts as your leaving group. Okay, that's your leaving group. And you form, and remember what functional group in this case, this is an ester functional group, where you get the R and the O and the C double bond O and then another R. I think I did that right. Yep. Just a little prettier, less chicken scratchy. Okay, so the nucleophile comes in, attacks the carbonyl, the electrons go up to give you the formal charge on the oxygen, but then it sort of reverts back by pushing the electrons back down between the oxygen and the carbon, but we spit out a leaving group, in this case a chloride, and you form that ester. So let's talk about the different things that affect reactivity with regard to this type of reaction. So first of all, there is the steric hindrance. We've talked about this before. So the relative reactivity of carboxylic acid derivatives. First of all, unhindered carbonyl groups are going to be more reactive. Unhindered carbonyl groups are more reactive. I apologize, I'm not having it, animate one line at a time, but we'll just talk through it. So if you look at this diagram here, this carbon has got 3 R groups on it. So it's got a lot of atoms in the way of the carbonyl. The nucleophile's got to attack that carbon in the carbonyl. Well, this has a lot of carbon atoms and hydrogen atoms that are just going to get in the way. So if I reduce that down to 2 R groups, it's a little bit more accessible. If I reduce it down to 1 R group, it's even more accessible. But if it's just a CH3, if it's just a methyl group, it's the most accessible. So that's the most reactive. But something else that affects reactivity is the type of substituent on the other side of the carbonyl. So yes, we've got our R group, that carbon containing hydrogen, carbon hydrogen atom containing part of it. But what's on the other side? Well, that affects the reactivity. And if that functional group is electron withdrawing, if it's electronegative atoms that kind of pull electron density away from that carbon, then it makes it even more reactive, because remember what's going on with this carbon is it's behaving like an electrophile, like a positively charged region. So this, you don't have the electron map in your handout there because, it's color coded and it's not much point in it. And it's even a little bit more challenging to see here, but remember that blue means positive. So the carbon in the middle, if it's more blue, it means it's more reactive. And so as you can see, as you go through these different functional groups, like acid chloride, that carbon right there in the middle is clearly a little bit more blue. There's more blue around that carbon in the middle than there is with the others. And that's because this chlorine is electronegative, so it kind of pulls electron density away from that carbonyl carbon, making it a stronger electrophile. Okay, so this is the order of reactivity. And this is something you should know, that amides are the least reactive, then esters, then thioesters, then anhydrides, and then acid halides, acid chlorides, same kind of thing. Okay, so make a flashcard or whatever, but you do want to learn that order. But it's based on, again, the electron withdrawing function or capability of whatever is connected to that carbonyl carbon. Okay. All right. Oh, one thing I want to point out before I move along is that you may be thinking, well, wait a minute, aren't nitrogen and oxygen also pretty electronegative elements? So wouldn't they be electron withdrawing? Well, that's true. But remember that they've also got these lone pairs of electrons that can actually engage in resonance forms. And so this lone pair of electrons can get donated and form a double bond with that carbon as the electrons move up onto the oxygen. So that kind of, again, tames the positive charge on that carbon because of the resonance forms, that it can actually share that lone pair of electrons with that carbonyl carbon. And the same thing with the oxygen. Same thing with the sulfur too, but it's just not as effective. Okay, and with the anhydride, you've got that oxygen, that's true. So it does have its lone pairs here, but it's also got to share those with this other carbonyl over here. So it's just less electron donating than with the ester, than like it is with the ester group. Okay, so yes, nitrogen and oxygen are electronegative, so they withdraw through the inductive effect in that way. But because of resonance forms that can be established with these lone pairs on those atoms, it overall is not very electron withdrawing. And you could even say it's electron donating to the carbonyl group. Okay. All right, so I got a small group activity for you today. So think about this with your neighbor. Based on what we just talked about, try and rank these from 1 to 4, where 1 is the least reactive and 4 is the most reactive. I'll give you a minute to do that, and I'll show you the answers. So the least reactive is the amide. Amides are the least reactive functional group that we looked at in that spectrum there. And because this one is more sterically hindered, it's got, you know, a secondary carbon next to the carbonyl, so it's the least reactive. And then the amide with the just the methyl group there, that's the little bit more reactive. But then the acid chlorides, these are both acid chlorides, but this acid chloride on the right is more sterically hindered. You got a T-butyl group; those are all methyl, 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 methyl. So that's more sterically hindered. So it's the next most reactive, and then the most reactive one is just the methyl acid chloride. All right, so hopefully that makes sense. Okay, so now the consequences of this, the differences in reactivity will dictate what kind of reactions and what kind of transformations can occur. So here's the bottom line of it. A more reactive acid derivative can be converted into a less reactive one. And usually we can start with, or the consequences of this, or the bottom line of this is that usually we can start with an acid halide or an acid anhydride and react it rapidly with anything, but it particularly acts rapidly with water to form carboxylic acids, or something else, something that's just more stable, less reactive. So for example, I can start with an acid chloride and I can make an anhydride, I can make a thioester, I can make an ester, or I can make an amide. If I start with an anhydride, I can't go backwards easily, okay, to make the acid chloride. I'm sure there's a way, but typically, you know, you go down, you don't go up the chart. So with an anhydride, I can react that with the right compound and make a thioester, or with a different compound to make an ester, or with a different compound to make an amide, and so forth and so on. So you get the idea that the more reactive the functional group, the easier it is to form a more stable or less reactive functional group. And that's really what we're going to see throughout the rest of this week, is how we start with things like acid chlorides or acid anhydrides, and we make these other functional groups like esters and amides. Okay, and that's what this chart really just kind of shows. If you start with an acid chloride or acid halide, they have certain names. If you react it with water, that's called hydrolysis, and what you get is you get the carboxylic acid. If you react it with an alcohol, it's called alcoholysis, and you get an ester. If you react it with an amine or ammonia, you get it aminolysis, and you get an amide as your product. Okay, you can react it with just with some hydride, and that just reduces it to something less oxidized, like an aldehyde or an alcohol. Or you can react it with those Grignard reagents that we described earlier in the course. And you can also get a substitution reaction where the Y group gets substituted with the R group that was part of the Grignard reagent. Or if you react it again with another equivalent of Grignard reagent, you get a tertiary alcohol. Okay, so that's what we're going to do today and tomorrow, and probably even Wednesday, is talk about these kind of reactions. Okay, so let's do an example. So we want to predict the products of the following nucleophilic acyl substitution reaction. All right, so we've got a thioester. This is a carbonyl that's connected to a sulfur that's got another R group on it, which is more reactive, less stable than an amide. So it will substitute with this amine to give us the amide. And really all I expect of you is just to know the final product, but I'll do a little bit of the mechanism as I talk about the answer here. Okay. So again, what we got is I've got this nitrogen with the lone pair. That's going to act as my nucleophile. It's going to attack that carbonyl carbon. Okay, so this one pair of electrons is going to move up onto the oxygen. And so the intermediate is going to be a tetrahedral thing. I've got the methyl group, and then it's attached to that carbon, which is now attached to this oxygen, which has formal negative charge. Okay, and then the sulfur, SCH3. And now I've got this N. I'm going to draw this little, so NCH3. And then it's got a hydrogen up there. It's got a hydrogen down there. And it's got, at this point, it's got a formal positive charge. Okay. So in this case, what's going to happen is, first of all, I'm going to, remember this has two lone pairs of electrons on it. So it's going to grab one of those hydrogens. The hydrogens are going to come off, or pardon me, it's going to donate those, the hydrogen is going to donate its electrons to the nitrogen. And then one of these lone pairs on the oxygen is going to reform the double bond. Okay, so I know a lot of arrows in there pushing electrons around, but as I said, what you really need to be able to do is come up with a final product. And so the final product is going to be the CH3 connected to the carbon, which is now reestablished that double bond with the oxygen to reform the carbonyl. So this is my leaving group. Okay, so that pair of electrons goes onto the sulfur. This is my leaving group. Okay, so I get rid of that sulfur substituent, and I attached nitrogen, and this now it has the hydrogen and the methyl group, and then the other product is hydrogen, sulfur, CH3. Okay, so this SCH3, after it grabbed that hydrogen, that makes for a good leaving group, and so that's where it is. Okay, so but the big thing is this is your product right there. You formed an amide. And the reason, the sort of the driving force of this reaction is that these amides are more stable, they are less reactive than the thioesters. Thioesters are a little bit more reactive than amides, so this reaction is going to go in the forward direction. Oh, yeah. So this is just the diagram that I was talking about. Thioesters are more reactive than amides. Okay. So you just get rid of the SCH3 and you add the amine. One of the hydrogens on the amine comes off and gets connected to the sulfur, making it a good leaving group, and you get the amide overall. That's the big thing. Okay. All right, so I got another small group activity for you. So now let's think about this again. Look at the reaction schemes and the reactivity spectrum there, and try and come up with the products here with your neighbor there, and I'll show you the correct answers in just a minute. Okay, so for this first one, what you start with is an acid chloride, an acyl chloride. Okay, they are very reactive. So if you react that with an amine, then you're going to break this carbon-chlorine bond, and you're going to form a carbon-nitrogen bond. All right, and then you're going to lose the hydrogen on the nitrogen. So you break that bond, and you form the carbon-nitrogen bond, and you form the HCl. It's just as a byproduct. Okay, you start with an acid chloride, and you end up with an amide. This is an amide. All right, so in the next reaction, as you can see, I just put no reaction, and that's because if it were to go forward, you would produce an ester. This alcohol would replace this amine group to give you the ester, but esters are more reactive than amides, so we know that this reaction is not going to go forward. Amides, what you start with, is more stable than what you would have ended up with. So that's why I cross it out, because you're not going to get those products because amides are actually more stable than esters. Esters are more reactive than amides. Okay, so reactions of carboxylic acid. So carboxylic acids themselves are actually not very reactive. So, but a lot of times you want to transform them into something else. You got to do something with it. So that OH group in the carboxylic acid is a poor leaving group, but you can convert it into a better leaving group. Okay, so those nucleophilic acyl substitution reactions on a carboxylic acid is difficult. So what you do is you increase the reactivity. So the reactivity of the acid can be increased by, first of all, you could use a strong acid catalyst to protonate the carbonyl. That's one technique, and we'll look at that in just a second. Using a strong acid catalyst to protonate the carboxyl, sorry. Or the other thing, we've seen this before, is you just make that OH a better leaving group by reacting with something. And there are lots of different reactants out there that we can use to make that OH, to convert that OH into a better leaving group. Okay. Okay, so one way to do that is to convert it into acid chloride. So conversion of carboxylic acids into acid chlorides. You can react it with this stuff called thionyl chloride, SOCl2. And we have seen this before when we were talking about primary alcohols and doing SN2 reactions with primary alcohols. This was one of the ways that we made that primary alcohol more susceptible to an SN2 type reaction. Okay, and it's the same mechanism. The SOCl2 essentially replaces the hydrogen in the OH. You can see that here, forming a chlorosulfite. And that chlorosulfite is just a much better leaving group. So at the end of the day, then one of the chlorines that was on the SOCl2 acts as a nucleophile with the carbonyl and takes its place. Okay, so the SOCl leaves, okay, ultimately forming just SO2 gas. So one of the chlorides is out there as well, floating around. But one of those chlorides acts as a nucleophile and forms a bond with the carbonyl to give us the acid chloride. So this is how you can take something that's not very reactive, a carboxylic acid, and transform it into something that is very reactive, an acid chloride. Okay, so as just describing the mechanism here, the COOH, the carboxylic acid group, is converted into an intermediate with a much better leaving group than OH. And then that intermediate reacts with a chloride via a nucleophilic acyl substitution reaction. All right, so the bottom line is that now the compound can be easily transformed into a variety of other derivatives. So as you saw from the previous chart, this acid chloride is the most reactive of the bunch. So now I've got something that can be transformed into a lot of different other compounds. So it's one way to take a carboxylic acid and to transform it into something, a lot of different other things. You kind of take a stop along the way by creating this acid chloride that's easily transformed into a lot of different other things. Okay. So that's one way. So this is another way to transform a carboxylic acid into an ester. Now this one is specific to, making an ester, and it's just one way to make an ester, but it's something we actually talked about before. So we're just in a way we're reminding you. We talked about how carboxyl groups are pretty good nucleophiles for SN2 reactions back when we were describing SN2 reactions way back in the day, right? Well, when that happens, you make an ester. So conversion of carboxylic acids into esters. Recall that carboxylate anion is a good nucleophile for SN2 when it's reacting with a primary alkyl halide. So that's kind of one of the limitations. This works really well if the ester is being formed with a primary alkyl halide, like iodomethane, like this one. Okay, it works pretty well, but that efficiency quickly runs away if you use anything other than a primary alkyl halide. Okay. So again, we're just kind of listing all these different ways we can transform carboxylic acids. We mentioned two of them now. Here's another one that's a lot more popular. It's called Fischer esterification. So if we want to make esters, this is a more generic, a more common way of doing it. Okay. It's Fischer esterification is the synthesis of esters by an acid catalyzed nucleophilic acyl substitution reaction of a carboxylic with an alcohol. Okay, so this is what I expect you to know, all right? Know the generic reaction. You have a carboxylic acid reacted with an alcohol with an acid catalyst. Remember that H2SO4 is a strong acid. And what you get is you get an ester and then a byproduct of water, okay? That's the generic reaction. Here's a specific one. So we can start with acetic acid reacted with ethanol with an acid catalyst, and you get this ester called ethyl acetate. Okay, the ethyl alcohol ends up where the OH was, and the rest of the molecule stays the same. Okay, so that's a specific one. So know how to convert a carboxylic acid and an alcohol into an ester via the Fischer esterification reaction. Now, that again, all I know is that you'll be able to predict a product, but I do want to go through the mechanism here. So this is the step-by-step mechanism of how this actually works. So the first thing that happens is that acid, we said this was acid catalyzed, so that acid, the hydrogen goes onto the oxygen in the carbonyl. We protonate the carbonyl, okay, forming that oxonium ion. And then the rest of the base, the rest of the acid is just the conjugate base is there. Okay, so a nucleophilic attack on the carbonyl by the alcohol, and this is step 2, subsequent cleavage of the pi bond, resulting in an oxonium ion, which is then rearranges itself after a proton transfer. So you can see it's a lot of words. So let's just follow the arrows to kind of really understand what's going on. So now your alcohol is your nucleophile, and it attacks the carbon in the carbonyl. Okay, forms that oxygen carbon bond. At the same time, one pair of electrons in this double bond move up onto the oxygen. Okay, and so as an intermediate, you get this tetrahedral intermediate. Okay, and so what happens is a rearrangement of the hydrogens, where the hydrogen that was on the alcohol is now going to go on the OH group that was part of the carboxylic acid, and it forms a water molecule, which we know is a good leaving group. This H2O is a good leaving group. And so it's going to do that. It's just going to leave. And that's what happens in step 3. So in step 3, the water molecule leaves. So this pair of electrons moves onto the oxygen. And at the same time, we reform the carbonyl carbon-oxygen double bond. Okay. And so I've got rid of my water. I spit out the water molecule. And so now I've got that characteristic ester bond, the carbonyl with the oxygen and the other carbon-containing group. I've still got this proton on the oxygen in the formal positive charge, but don't worry, that's going to go away. So, oops. So now just that Lewis base that was hanging around from step 1 takes away that, because we have to regenerate. This is an acid catalyzed, right? So we got to regenerate the catalyst. So I just regenerate that catalyst by the base taking that H plus back, and you get the ester as the product. Again, I don't expect you to know, all the pieces and parts of this mechanism. Just be able to predict the products. All right. So let's do an example. So how is the following ester prepared from the corresponding carboxylic acid? So you just had to do a little reverse engineering. Okay, so remember that what you do is you kind of split the molecule like this. The carbonyl part, that comes from the carboxylic acid. And then this part, I'll change color so that it's a little bit more distinct. So this part comes from the alcohol, because that's how you generate through a Fischer esterification. You react a carboxylic acid with an alcohol to get the ester. Okay. So the reaction here was something like this. We have the CH3, CH2, CH2, and then the C double bond O, and then this was a OH, right? I said that was the carboxylic acid, and I reacted that with an alcohol, so it must be HOCH3. Okay. So you could say that that oxygen and that hydrogen split off to form your water molecule, and then you establish this bond between that oxygen and that carbon. Okay, that's that bond right there. Okay, so these two things, this carboxylic acid and this alcohol, reacted to form this ester. Okay, so that's kind of what I expect you to do. Either to go forward, or if I give you the carboxylic acid and the alcohol, that you can predict the product, or I would expect you to be able to reverse engineer it. If I give you the ester, can you reverse engineer it and go backwards to tell me what the carboxylic acid and the alcohol were that, you know, reacted together to create that ester? Okay, so again, this is just a little nicer handwriting. Butanoic acid reacting with methanol, acid catalyzed to give you the ester. Well, by the way, I'm not even doing a section on naming this week, because there's, you know, so many different functional groups and so many unique rules. We're not even going to worry about naming them. Okay, so here we go again. I got another small group activity for you. So now I give you the carboxylic acid and I give you the alcohol. Remember that this is a tert-butyl group. Hopefully you remember what that looks like. Acid catalyzed, what do you think the ester is going to be? So think about it, talk about it with your neighbor, and try and come up with a product. Okay, so there you go. So the T-butyl alcohol is your alcohol. This this would be benzylic acid. Oxygen acts as the nucleophile against the carbonyl, forms the bond. And so you get that this is your T-butyl group right here, tertiary butyl. It's got 4 carbons with a carbon in the middle connected to 3 other methyl groups. Okay, and then you eliminate a water molecule in the process too, composed of like that OH and that hydrogen. That's your water molecule. So you form the covalent bond between that carbon and the oxygen and the T-butyl alcohol.